Hello, I am going to be recording the next couple of videos just so we get exactly what I would like you guys to know in this class. We're going to start here with chapter 2, organizing data, and I have my little memes, because I love my memes. I don't always graph my data. Oh, wait, yes, I do. So pretty much when we do any kind of data analysis, we always want to start with seeing what the data looks like. And in order to do that, we need to do some kind of organization, because if you just have a bunch of data points, there's not much you can say about it. But if you have it in some kind of a chart or some kind of a graph, then you can kind of visualize what your data looks like, how it's shaped, and we'll go into all of that in this chapter. So the first thing I want to talk about is what a frequency distribution is. That's, for one thing, to start with, we're actually going to talk about qualitative data. And that is just a list of each distinct value, and in this case, category, because we're actually talking about categorical data first, and each frequency. So to start with, say, our Skittle colors. So you know how much I love Skittles. So we can start with the red. So let's say we had a bag of Skittles and this was our frequency for it. So we have red, yellow, green, orange, purple, and we had 17 red, 15 yellow, 11 green, 10 orange, 7 purple. This is just a frequency table. And when we have our frequency table, this is just not really telling me too much. It's organizing the data a little bit. It's hard to kind of see. I mean, I can glance at it and I go, oh, it's red that we have the most of and purple we have the least of. That's about all I can tell about that. So my next thing that I want to do is what's called a relative frequency distribution, which we kind of did last time when we were doing the last Skittles. Is we did a relative frequency distribution when we divided everything by the total. So that's exactly what we're going to do here. So we have our Skittle color, our frequency, and now our relative frequency. So you'll notice that each one of these is divided by 60. So that way we can find out, in a way, what percent of the Skittles in this case are red, yellow, green, orange, purple. So, I mean, I knew that red was my most at 28.3%. I knew that my least was purple with 11.7%, but now I actually do know those percentages. And if I even wanted to look at these in percentage form, I can do that also. I'm not real big on which one you give me. It doesn't make any difference to me if you give me percents, but make sure if you do give me percents to write that percent sign on there so that I know it's 0.283 or 28.3%. So let's talk about how we go about doing this on our calculator. So when we bring up our calculator, the first thing we want to do is we want to enter all of our frequencies. So in order to do that, you're going to go Stat, Edit, and then I want to enter my lists. Now I don't have anything in my lists. If I did, I want to go up to, I want to highlight where it says list 1, and I could just hit clear, enter, and that would clear anything that was already in there. So what I'm going to do is list 1, let's say I have my frequencies. I'm just going to make some up. Let's say that I have 13, 12, 18, 6, and 5. Now, I don't know exactly how much that is. Let's see, that's 25. Let's say 1. So I have 25, 19, and 11, or 18 and 12. So it looks like I have 55 in my list that I made here. So what I'm going to do is over here, I'm going to list 2. Then I'm going to cursor up until my L2 is highlighted. Then I press L1, so that's second 1, to bring up L1. Now you'll notice underneath here, you'll notice that L1 has come up. And then I just divide by that total, which was, what did I say, 55? divided by 55. And there I get my relative frequency. So now in one fell swoop, without taking each one going, okay, 13 divided by 55, 12 divided by 55, and so on and so forth, I can all at once get all 5 of my relative frequencies. And so this, now you have your frequencies and your relative frequencies. Now you can make sure that those are, another way I can actually tell what my sum is I could actually go second stat, go to math. If I wanted the sum of those, see number 5 is sum, 5. Oops, that's not where I wanted it to be. Let's quit out of this first and then go list, math. I want the sum of list 1, just to make sure that I definitely have 55. There you go. So I can do that each time. I can also do that straight from the stat menu. I could go over here to list 3, and let's say list 3 equals second L1 divided by, then I can go to second stat, which is lists, which tells me about the lists. Go to math, go to sum of list 1. This is going to give me exactly the same numbers, as you notice. So this way I don't have to add those numbers up in my head. I can actually do it this way. So now that we have our frequencies created, now let's talk a little bit about, oops, that went too far, about how we visualize these distributions. Now, first of all, we can look at a skittle color distribution using our pie chart. Now, the pie chart tells us the relationship of each frequency to the whole. And you'll notice what I put here is the percentages instead of the actual frequency, because that's what this really tells me. This is now the relationship. Red is 28%. I don't know how many reds there are. I don't know how many there are total. But what I do know is that red is the majority. And I can tell that just by looking at this. I can tell that purple is the least. So I can do that with at just a glance. And that's what is nice about pie charts. To make a pie chart, we'll actually be making one in class, but to make a pie chart, and the way that I go about this is if I go back here, no, your calculator doesn't do it, but if I go back here, the way that we can make a pie chart, we can actually use our calculator, which is really nice, a little bit. So what we're going to do is we're going to take these frequencies, and in order to find the number of degrees that each one represents in a circle, so remember a circle is 360 degrees. We're just going to take this and we're going to multiply this. So we take the relative frequency and we're going to multiply by 360. So if I look back here at my list, I'm actually going to clear list 3 out because I don't need that anymore. I'm going to take list 2 now and multiply by 360. So I'm going to go up, highlight list 3, or actually highlight list 3. And say, this is going to be list 2 times 360. Now you notice we get these. I'm just going to round these off a little bit. So I have 85, 79. Oh, this isn't the right ones. This isn't the same thing. Okay. It's not the same as those. Okay, let's do our example. We'll do our example down here. Okay, so we have 13, 12, 18, 6, 5, 1. And then this is 24%, 22%, 33%, 11%, 9%, and 2%. And our degrees are 85. And like I said, I'm just going to round these off because there's no reason to try and do this any other way because, see, that's 33 and this is 7. So when I'm doing this, what I want to do is I have a circle and I start with 0. Now, when we do this in class, we're going to have one that's already shown with degrees, but I'm just going to kind of eyeball it. 24% is 85 degrees, so it's just under 90 degrees. So I'm just going to do that right there and go 24%. And then this next one is 79 degrees from this point. So 90 would be about right here. So we want 79. So we're probably going to be right here. I'm just, like I said, I'm eyeballing this right now. And then now we want 118 degrees from this point. So let's see, a 90 degree angle would be here. A little bit more than that would be like about there. So this is 33%. And then we want 39 degrees. So let's see, a 45 degree angle from this one would be about here. We want a little less than that. Okay, so this is the 11%. And then we want 9 and 2. So my 11 doesn't look as, my 11 looks bigger than my 9. Let's make that a little better. Okay. So like I said, I just kind of eyeballed that one, but we're going to have one in class where we do it a little bit better. But I just wanted to kind of give you an idea of how a pie chart was made by hand. Now you can also use Excel, really quick in Excel to use them. That is totally fine with me. We won't be actually looking at something like this on an exam, but I just wanted you to see exactly how it looks. Now the second thing we have here is our bar graph. Now our bar graph, it more focuses on how much each category has. So it really looks at the frequency, whereas this one looks at more the relative frequency. This one really looks at frequency. Not to say you can't make a relative frequency bar graph, because that's just a change of this right here. But what we have, and we can actually see just by looking at this, okay, red's got the most, and we go down from there. We can look at how that goes down and down and down. Now, when I say that, I want to be very careful, because would it matter if red was first? Maybe I could put these in alphabetical order and green would be first. Maybe I'd put these in my favorite Skittles and I would have red and then purple and green and orange and then yellow. So, I mean, I could do this any way I want because it's categorical data. Now, that is why we have space in between here. This space indicates categorical data. Now that's going to become very important later on. We start talking about histograms, because that's one of the major differences between histograms and bar graphs. So now let's move on and let's start talking a little bit about what we do with numeric data, or what we call quantitative data. So what I have on this one, you'll notice I have days to maturity for 40 short-term investments. Now, these investments are everywhere. I mean, if I look at this and I just stare at it, I go, there is absolutely nothing I can do with this data. Just kind of going, okay, a bunch of data. I don't know what to do with it. I can't visualize it. I really don't know what's going on. So really what I need to do is I need to organize this data. And the first thing that I'm going to do is I'm going to create a frequency table. Now, I'm going to decide where to group it, because it wouldn't make any sense to take each number, because I have everything from numbers in the 30s to numbers in the 90s. So what I'm going to do is I'm going to regroup them. And I'm going to call this what we call limit grouping. Now, limit grouping is more used for discrete qualitative data. Now you know why we had to learn about all that. So limit grouping is for discrete data. that is where we can go from 30 to 39. There's nothing in between 39 and 40. So we know exactly where the cut is. So we go from 30 up to 39, and including both of those, 40 to 49, including both of those. So it's 30 through 39, 40 through 49, etc. Now this is the first kind we're going to do. We're going to be doing another kind in a minute. So we count these out. We do our tallies. No great way to do it. One of the things you can do with your calculator is if I have a bunch of data. So let me just take this data that we already have. And because I don't want to type all that data in here right now. But if I have all this data, so I have this data, let's say these are a bunch of data points like this. Well, I can't see that. I don't know what's going on. And if I have even more, it's even harder. But what I can do is I can actually sort this data. And to sort the data, you want to go to Stat. So I hit Stat. And you see where it says Sort A? So Stat, Sort, oops, not SOPT. Sort A. So that's number 2. And then I'm going to tell it list 1, second 1. And it doesn't matter if I do that. Okay, done. So it just says it's done, and you say, okay, fine, you're done. So then if you go back into Stat Edit, you will see that now they're in the correct order. So now that they're in the correct order, now I could easily count all of these. So if I put all of this data into my calculator, which I'm actually not going to do right now, then I could easily figure out the frequency for each one. Because I said, okay, if I want to go 1 through 5, I could have 1 and 5. If I want to go 6 through 10, then there's one of those. Okay, 10 through 15, 2, and 15 through 20, I would have 1. So I could actually see that particular frequency just by doing that. And it makes it just a lot easier to do if you sort your data when you're trying to do something. Okay, so, and you can also then enter your frequencies in the calculator and divide by the number of data points you have, and you can get your relative frequency, just like we did with categorical data. Now, we wouldn't want to do that with these numbers that are in my calculator already, because now those are actually the numbers we have, not the frequencies. And that's the difference. You want to be very, very careful if you actually have the numbers or the frequencies. Okay. So here's another type. This is what we call cut point grouping. And cut point grouping, we have to be a little more careful because the data is continuous. So in this case, it's 0 to under 25,000. So that means that it's up to, but not including 25,000. That means that 24,999.9999 would actually go into this first category. Therefore, what we would actually want to look at, if we had 24,999, is we are looking at numbers that are up to and can be as close as possible to 25,000, but not including 25,000. Once we're 25,000, we're now in this category. And that's how we do cut point grouping. And you'll notice that generally speaking, when we do cut point grouping, and it can be done a lot of different ways, you can actually do ending to the right or ending to the left. So what we've done is we've done what we call left inclusive, which means we include the left number, but not the right number in each group. And that's going to be really important when we go to make histograms. So this is what we call a left inclusive frequency table. And you'll notice we've done the same thing. We've got our frequency in millions, and then we've done our relative frequency just by dividing each one of these by 95. So now let's start talking about these histograms that I keep talking about so much. So looking at histograms, you'll notice something about them. Number one, they're very similar to bar charts, but the bars have to touch, and that indicates the quantitative nature of the data. So that's one really, really important thing. I'm kind of picky about histograms. I want you guys to know that now. I'm not picky about much, but about histograms I am. There are certain ways that histograms should be done and should be done correctly. One of those things is the bars have to be touching because you are showing a direct order. 15 comes before 20, comes before 25, 30, 35, 40. So you're showing that order of things when you put them together. Number two, one other thing that's very different is the horizontal axis is a number line. Now notice in a bar graph, we put those labels, green, yellow, etc., right? Now I don't want to write in here 15 up to but not including 20. I don't want to write that there. So what I do is this horizontal axis should be a number line. This is just a number line. And what you can do is in single value grouping, the number goes right in the middle. I haven't given you an example of single value grouping yet, but I will. Now, the distinct value of the observations is centered. That is the only time that this is centered. That the label should be centered underneath the bar. For limit grouping or cut point grouping, we use the lower class limits or cut points to label the bars at the beginning of each bar. So that means that this bar right here indicates 15 to under 20. This one is 20 to under 25, etc. Or it could be 15 to 19, 20 to 24, 25 to 29, depending on, this is, and we don't know what kind of data this was. If it was discrete, we would do this. If it was continuous, we would say this. Because in discrete data, we won't have anything between 19 and 20. In continuous data, we could have 19.99. That would still be in this category. Where would 19.99 go here in discrete? We don't know. That's why it has to be discrete data that you use that for. If you have decimals, you have to use this one. So you'll notice each one of these goes at the beginning of the bar. So this one indicates 20 up to 24 or 24.99, however you want to look at it. This one goes 25 to under 30. This one, 30 to under 35. And this one, 35 to under 40. And you'll notice on the y-axis, this is a frequency or relative frequency, and I will let you know which one I want. So you have to be really careful. Am I asking for frequency or relative frequency? And then each vertical bar goes up to that frequency. Okay. So let's look at the days to maturity problem. Now you'll notice something. Here's A, the frequency histogram, and B, the relative frequency histogram. The frequency histogram, and you'll notice it was nice. It kept the 0, 10, and 20, even though they weren't really there. Now the frequency histogram, it tells me 3 were in the first group from 30 up to, but not including 40. So remember this one was 30 to 39. This one was 90 to 99. We didn't have 100. So you'll notice that the last one is labeled as what the next would be. Okay, so what the next one would be the last label. Because if we went on, this next one would be 100 and up. So we know that that goes up to, but not including 100. So it goes up to 99. Then we look at this relative frequency one. And so we look at this, it's like, ooh, that looks like about, I don't know, 7.5% right there. We aren't exactly sure. It's a little bit more difficult. But I want you to look at the shapes of these. What do you notice about the shapes? Think about that for a second. You should notice that the shapes are basically the same. And the only difference is the y-axis. That is the only difference between these two. So these are kind of things you want to look at when you're doing histograms. Are we doing frequency or relative frequency? And really the only difference is how you label this y-axis. So the easiest thing to do if you make a mistake, you can always just change this right here to something else. So now we're going to talk a little bit about dot plots. Now dot plots are just like this. Now a dot plot is made up of where we are. So this is the prices in dollars of 16 DVD players. This was probably a really long time ago, because I don't think DVD players cost this anymore, because nobody really wants them anymore, because we might as well just stream everything. So this was the price of DVD players maybe in, I don't know, some year, 10 years ago or so. And so if we're looking at this, basically we just go 210. We put the 210 dot there. 219. We put a dot there. 214. We put a dot here. 197. We put a dot here. 224. We put a dot here. 219. Oh, we already had a 219. We put another dot here on top of it. So we go like that until we've got all of them done. And we end up with a dot plot, which kind of gives me sort of a shape, but not really. I can't really see the shape of that very well, simply because I don't have enough repeats in this. So it kind of gives me a shape, but it's not the greatest. I don't use dot plots a lot unless I have a lot of data and I have a lot of repeats. Then it's kind of useful. You can actually do two dot plots and compare two things of data, and you can kind of see their shapes side by side. You can put one on the top and say one on the bottom and see what you're doing. It's not something that I use often in statistics, but it's really something that you need to see. It's a quick, easy way to kind of look at the distribution of your data without making a histogram. Okay, stem and leaf plots. So the stem and leaf plot this to me is probably one of the most useful graphs that we have, because this gives me the idea of the shape like a histogram, and it actually puts the numbers in there too. It kind of uses the numbers as the dots, which I think is a lot more useful. So in a way, I can see the data much more easily. So here's those days to maturity that we had. And what's really nice is, let's say I have 2-digit data. That's the easiest thing to make a stem and leaf plot out of. Because our first step right here, so here's my first step, write all down with the last digit. So it looks like I've got some 3s, 4s. I kind of know what's in here already. I've already made the histogram. So we have 3s, we have 4s, we have up to 9s. So what we do is we write all of these down in order. And you have to write them all. If you have only 3, 4, 5, 7, and 9, you still would have to keep the 5 and the 8 in there. Even though there's not going to be anything on the other side, you can't skip any. You have to keep them all in place. So let's say this 47 wasn't there, you'd still have to have this 4. And so we write down all of these. We draw our vertical line. Then we write the last digit. So we only leave one digit, and I'll talk about that in just a minute. But you'll notice that in here we only have 2 digits. So this one goes before the line, this one goes after. That's how it works. So then we write in the last digits on the appropriate line. So I'd go in here and I would put 70 first. I put a 0 to represent 70. So I go up to this one, 64. Oops, I went down anyway. 62, 75, 57, 51, 64, 38, 56, 53, and 36. So you can see how I'm going through these. So I go through each one of my pieces of data and I do this. Then I reorder them. Now another way to do that is if the data is in the calculator, you can sort A first, then make your stem and leaf. Now what that does for you is that allows you to skip this reordering step because everything will already be sorted. So everything should be in order. You just go 3, 6, 8, 9, 4, 7. So this data should always be in order. And that's one of the things I'll be looking for. But what's really nice about a stem and leaf plot is I can basically kind of see what shape it makes. I can do that. I can say, oh, where's the number in the middle? I can see kind of where the middle is. It's in here somewhere. So I can kind of see where the middle is. I can see a lot of things because I have those numbers in there. When we get to chapter 3, we'll be able to do things like I could easily find the mean. No, I can't find the mean easily, but the median and the mode I can easily find from the stem and leaf plot without actually going through too much trouble. So let's talk about what happens when we have more than 2 digits. Now remember, I said write down all but the last digit. And this is those DVD players in 2007, probably. Okay. So when I'm writing down all but the last digit, I'm looking at it like this, leaving these last digits. So what I really want to look at is my numbers are actually 19, 20, 21, and 22. So the only one that's 19 is 199. So I have 20 and I put all those down. Now I've already reordered it also. But looking at this one, this is what we call one line per stem. So these are the stems. And each one of these is called a leaf. But this is one line for each stem. So I have one line for the 19s, one line for the 20s, one line for the 21s, and etc. Here, I have 2 lines per stem. So on the first line, I put 0 through 4s. On the second line, I put 5 through 8s. So notice, when I have 20, I break it up to the 0 to 4s, and this is the 5 to 8s. It does not break up where it breaks up evenly, because that wouldn't tell me anything. And it doesn't break up where anything else at the 6s or 4s or 5s or anything else. So it breaks up between the 4 and the 5. So here, 0 to 4s, 5 to 8, 5 to 9. Whoops, not 8, 9. I meant to say 9. I've done this 3 times too. 5 to 9s. And then the last one, 0 to 4s. I added the last 2 on there, really didn't need to. So we can look at the shape of this once again. And you'll notice this just isn't enough. I mean, I can kind of see the shape, but it isn't enough stems to really see the shape of the data. Here I can really see what's going on. And in here, this one I can't. This one I can. So in this case, it's much better to have the 2 lines per stem. So I've talked a little bit about shape of distributions, but let's talk a little bit about it. Now remember, the distribution of a data set, it's either a table, which we talked about our frequency distributions, our graphs, we've done histograms and stem and leaf plots and dot plots and everything, or it can also be a formula. Now that's kind of later on. Chapter 5, we'll start talking about a few formulas that we can do to provide the values of the observations and, of course, how often they occur. So looking at this, so here we have a relative frequency distribution, and it has an approximating smooth curve. So this curve is just an approximation. This is a distribution of, I believe this is heights of college women, from what I remember. And so I can kind of see how this is distributed. And this is a bell-shaped curve. It's symmetric. Also, some people call it mound shape. But this gives you an idea. If we do an approximating smooth curve, I've kind of been doing it this whole time. And we get an idea and we go, okay, well, that kind of makes a little curve, a bell-shaped curve. So let's look at a few different distribution shapes we might find. So this first one, these bell-shaped, that's the first one I looked at. That's heights. People's heights are often bell-shaped. Another thing is triangular. Triangular is very similar to bell-shaped, but it doesn't go off like this the way that bell-shaped does. So triangular is the sum of two dice, is actually a very triangular distribution, which again we'll talk about in later chapters. Uniform distribution, that is everything is equal. So rolling one die, theoretically, you have a 1/6 chance. So it should be you roll ones a sixth of the time, twos, threes, fours, five, sixes. So that's the one die. And that kind of goes like that. Now a reverse J shape might be a really hard test. Okay, where most of the people didn't score well, but a few people did really, really well. Okay, and here's an easy test. Okay, not very many people scored low. Everybody scored super high. Everybody got 100. Most people got 100%, but a couple people got less than that. Okay, these are, so a reverse J is just a really extreme case of what we call right skewed. So extreme right skew. So normally these are the big ones we look at. We look at bell-shaped, we look at right skew, and we look at left skew. These are our main three shapes, but we'll talk about that in just a second. So looking at the right skew, income is very right skewed. And so most people are around in here somewhere, right? And here's your 1%ers. Here's the rich people. They hang out over here. They're skewing the mean. So the average kind of gets pulled up by these people, but most people are in this normal area right here. And left skewed, we can think about birth weights. So babies. So most babies are born in here, in this area, but then you have the preemies that are born over here. So, and then we could have what we have, bimodal data. A lot of grades are bimodal. So let's say that these are F, the D's, the C's, the B's, and the A's. A lot of times I'll get this happening in some classes. I'll get lots of B's and lots of D's, and I'll have bimodal data. That happens quite often sometimes. Or we could have multimodal. And notice I said time. Multimodal, this is like something cyclical. We have data that kind of keeps going up and up and up and up, seasonal things. So we just finished the holiday season. So think about that, what sales we're doing. Okay. All right, so let's talk about population versus samples. So if we have a population, this means we know something about everybody in the population. So let's say that we're taking a look at household size. So let's say this is a population distribution. Actually, these both are. Of household size. And of course, the smoothing curve that we kind of put around it sometimes. So what kind of skew is this? So we see that this is what we call right skewed. If you get right and left skewed mixed up, it's where the tail is. So we call this right skewed because it's being pulled to the right by these few outlying observations. So most people, household size are 1, 2, or 3. And then, of course, you get a few people, a smaller percentage of the people who are over here. So if we look at this, we can see how this is distributed. If this is the population distribution, this is basically everyone in a population. So this could be college students. I don't know. This could be certain college students at a certain college. It could be a finite population, and we know something about the entire population. However, if we go out and let's say we want to get some samples. Now you'll notice this is the real distribution over here in blue, and you'll notice that the sample distributions are different. So let's say we all go out, we have 6 people, and 6 of us go out and we get some kind of distribution. We get some kind of sample. How many people live in your home? Okay. And we do that, and this is what we get. So you'll notice this is slightly different. This one's pretty close, actually. Okay. We got a little more of the 3s, so you'll notice the 3 is a little bit bigger in this one. This one, notice that 7 is none. So this sample didn't even include anybody with more than 6 people in their household. Neither did this one. This one didn't either, but it also made 5 and 6 the same. And this one has a lot more of the 2s and the 1s. And look, 3 is actually less than 4. So you can see how each one of these samples is different. Because of course, if we ask different people, we're going to get different answers. So every time we take a sample, we are understanding that we are losing some freedoms. We are losing some of the original traits of the population. And we know that. And we know that these are simply estimations. We know that. And we have to accept that. And that is really what part of statistics is we're going to be finding samples, and that's what inferential statistics really does. We take our samples to make inferences about the population, and most of these are pretty close. They're all skewed right. They all kind of have the basic shape that is the same, and that's kind of what we're looking for. So, for a simple random sample, and you guys know what that is, the sample distribution approximates the population distribution. Now, the larger the sample size, and this kind of makes sense, the better that approximation tends to be. If we go to 5 people, who knows what we're going to find? If we randomly select 5 people from a college and ask them how many people are in their home, that's not going to tell us, be a very, very good approximation at all of how many people actually live in the homes of these college students. So that is all for chapter 2. We will be doing a lot more in class, and so I will see you later.